possibility trees and the multiplication rule. Please take a look at this. If an operation consists of k steps and the first step can be performed in n1 ways, the second step can be performed in n2 ways, and so on, the kth step can be performed in nk ways, then the entire operation can be performed in n1 times n2 times and so on times nk ways. Actually, it's exactly what we used when we counted the number of elements in this sample space over here in example 2. So we roll 2 dice. How many elements are in the sample space? So note that in order to find the number of elements, either we list all elements or we simply use the multiplication rule. Operation number 1 can be performed in 6 ways. Operation number 2 can be performed in 6 ways. So the entire operation can be performed in 6 times 6 ways. Folks, any questions here?
Is that only assuming independence between the 2 dice?
Yes, we assume independence. We assume that experiment number 1 completely independent from experiment number 2. Over here, a typical pin is a sequence of any 4 symbols chosen from the 26 letters in the alphabet and the 10 digits with repetition allowed. How many different pins are possible? Guys, who can answer this question?
Would it be 36 to the 4th power?
36 to 4th power, because we have 26 letters and 10 digits. 26 plus 10 is 36. And our pin consists of 4 symbols. So it's 36 times 36 times 36 times 36, which is 36 to 4th power. So it's exactly what is written here. Next. Suppose that a repetition is not allowed. How many different pins are there? Anybody? Now repetitions are not allowed.
36 times 35 times 34 times 33.
Absolutely. It's 36 times 35 times 34 times 33. Because, let us go back to what is written here. Operation number 1 can be performed in 36 ways. However, once operation number 1 is performed, we no longer have 36 ways for operation number 2, because 1 element is already taken for position number 1. So second step can be performed only in 35 ways, third in 34 ways, and fourth in 33 ways. So it's 36 times 35 times 34 times 33. The second question is absolutely straightforward. If all pins are equally likely, what is the probability that a pin chosen at random contains no repeated symbol? We just divide 36 times 35 times 34 times 33 by 36 to 4th power. It's exactly what is written here, over here. Any questions?
Was the last probability like 36 times 35 times those last two? Is that a permutation or
well, it's yes, it is permutation. We will
okay.
discuss it, but this is a so-called R permutation. We discuss, yes,
Okay.
we discuss this type of permutations over here. So we do not permute all elements. We permute only 4 elements out of 36. So
Okay.
these are so-called R permutations. We'll discuss it at the end of today's classroom meeting. Now, next, possibility tree. Please take a look at this. Example 1. Teams A and B are to play each other repeatedly until one wins 2 games in a row or a total of 3 games. Question: how many ways can the tournament be played? Let us draw the following possibility tree. Winner of game 1 is either A or B. If winner of game 2 is A, then we stop here because we have 2 wins in a row. If winner of game 2 is B, we continue. Here, if winner of game 2 is B, we stop. If winner of game 2 is A, we continue. Game 3. If winner of game 3 is A, we continue. If winner of game 3 is B, we stop because we have 2 wins in a row. Similarly here, we stop if A, we continue if B. Game 4. If winner is A, we stop. We have 2 wins in a row, and by the way, 3 wins in total. If B, we continue. Here, if winner is A, we continue. But if B, we stop because we have 2 wins in a row and 3 wins in total. Finally, no matter what is A or B here, we stop because we stop if A, since we have 3 wins for A. We stop if B, because reason number 1, we have 2 wins in a row. Reason number 2, B wins 3 games. Same is here. Now let us count the number of tournaments. 1, 2, 3, 4, 5 here, and same number here. 5 plus 5, 10. The total number of tournaments is 10. Lastly, assuming that all the ways of playing the tournament are equally likely, or what is the probability that 5 games are needed to determine the tournament winner? So here 5 games means this. We have 4 divided by 10. It's exactly what is written here, or 2 over 5, 40%. Now let us continue our discussion of the multiplication rule. Permutations. A permutation of a set of objects is an ordering of the objects in a row. For example, the set of elements A, B, and C has 6 permutations: ABC, ACB, CBA, and so on. Question: Suppose we have n elements where n is an integer greater or equal to 1. What is the number of permutations of a set with n elements? The answer is n factorial. But guys, who can explain me why we have n factorial permutations of n elements?
Because in each
Yes.
place we can have an element, and then and then at other places we have n-1, n-2, n-3 elements, and at last we have one element which is equal to n factorial.
Absolutely. We use the product rule. Let us go back to the product rule once again. It's over here. So the first step can be performed in n ways. Now, once we perform step number 1, one element is taken. And remember, repetitions are not allowed. We are talking about permutations. So for step 2, we have n-1 ways. For step 3, n-2 ways, and so on. So it's n times n-1 times n-2 and so on times 1, which is n factorial. So please take a look at this problem. How many ways can the letters in the word computer be arranged in a row? Anybody?
8 factorial?
In 8 factorial ways, because we have 8 distinct letters. Okay, B, how many ways can the letters in the word computer be arranged if the letters C, O must remain next to each other in order as a unit?
Is that 7 factorial?
7 factorial. Why is that?
Because now CO is 1 unit. And
exactly. So now we think about CO as a single element. So we have element number 1, and number 2, number 3, number 4, 5, 6, 7. It's 7 factorial. Okay, C. If letters of the word computer are randomly arranged in a row, what is the probability that the letters CO remain next to each other in order as a unit? What's the answer?
1/8?
1/8, because it's 7 factorial divided by 8 factorial. So it's exactly what we see here. 8 factorial, 7 factorial, and then 7 factorial over 8 factorial, which is 1/8.
Then what's the difference between B and C?
Oh, B and C, in B, we count how many ways. In C, we count probability.
Oh.
Probability is a fraction. The number of elements in an event divided by the number of elements in the sample space. So B and C are different. C is a combination of A and B. The number of elements from A is denominator. The number of elements in B is the top of the fraction. Next, an R permutation of a set of n elements is an ordered selection of R elements taken from the set of n elements. And the formula is, for position number 1, we have n possibilities. Since one element is taken, for position number 2, we have n-1 elements, and so on. For the last position, we have n-r+1 possibilities. Note that what is written here can be rewritten as n factorial over n-r factorial. Any questions here?
Why is there a... I can see why the +1 is there to stop it from going to 0, R from going to 0, but I don't know why it doesn't make it... why is the 1 there?
So probably one way to answer your question is the following. Imagine that instead of R, we have N. the number of n permutations, and know that n permutation is the permutation that we discussed previously, correct?
Yes.
The number of n permutations is n factorial, correct?
Yes.
Now see what happens to this term if r is equal to n. We have n minus n, which is 0, plus 1, which is 1. So the last element is 1, correct?
Yes.
So this is why we add 1 at the end. And not just n minus r, but n minus r plus 1. Was that your question?
Yes, thank you. I think we're good.
Mm-hmm. Guys, any other questions?
So what's the difference between n and r, I guess, is my question.
Well, r is lesser or equal to n. For example, if n is equal to 3, we have 3 objects. The number of ways we permute these 3 objects is 3 factorial. However, if we don't want to permute all 3 objects, but we want to permute just 2 objects, these are not permutations, these are 2 permutations. Take a look at this, A, B, C. Compare this example and this example. In both examples, we start with 3 objects, A, B, and C. But these are 3 permutations that we call permutations. These are 2 permutations.
Well, that's 3 factorial.
By a coincidence, this is also equal to 3 factorial. But in order to find the number of 2 permutations, we do not use 3 factorial formula. We use this formula, which is the same as this.
And then that, so what's the difference in those 2 problems then? What?
Well, because this set is the, let me put 2 slides together. This set is different from this set. These are totally different sets.
Okay.
Correct? So
Okay.
in order to find the number of elements here, we use the n factorial formula. To find the total number of elements here, we use this formula. Either this formula or which is the same this formula.
Oh, okay. Because the order matters.
Does this answer your question?
I think so, because the order matters in that case.
Order matters here and order matters here. But here we choose 2 elements out of 3. Here we choose 3 elements out of 3.
Okay.
This is what makes the difference.
Okay, I see. I got it.